In this lecture, let me solve a problem and an example for you for computing the cubic spline for some data. So let me write the example here. If f of x be equal to e to power of x, okay, then find a cubic natural spline. When we say natural spline, it means that we use the first part of the free conditions. I mean, s double prime at 0 and at x0 equal to s double prime at xn be equal to 0. These conditions is called natural conditions, and the natural spline, in fact, is a spline with natural conditions. Okay, so find a cubic natural spline such that interpolate f of x at xj equal to 0, 1, 2, and 3. In fact, x0 should be 0, x1 should be 1, x2 should be 2, and x3 should be 3. Okay? Now, if we want to solve this problem, first of all, you have to compute y0. y0 is f of 0 and is equal to 1. This is f of x0 equal to f1, and this is f0, f0, and it will be 1. y1 is equal to f of x1, and this is equal to f of e, and this is e. y2 is equal to f of x2, this is equal to f of 2, and this is e squared, and y3 is f of x3, this is f of 3, and this is e cubed. Okay, so in fact we have this table. Now, because we have the natural conditions, because we have natural, so we should use s double prime at 0 equal to s double prime at 3, and this should be equal to 0. Now, we have to find Sj of x on interval xj minus 1 and xj for j equal to 1, 2, 3, for j equal to 1, 2, 3, such that Sj of x be equal to yj plus yj plus 1 minus yj over hj plus 1 minus 2mj plus mj plus 1 over 6 times hj plus 1 times x minus xj plus mj over 2 times x minus xj squared plus mj plus 1 minus mj over 6hj plus 1 times x minus xj cube. Okay, now because we used the natural condition, so m0 should be equal to m3 and should be equal to 0. We have used natural condition, so m0 should be m4 m3 and this should be equal to 0, and for m1 and m2 we shall solve the following system. And what's the system? The system is something like this. If you refer to the previous lecture, you can see that the in fact the system should be something like this: 2 2 2 2 here, and 0 0 0, mu 1 lambda 1 0 0, mu 2 lambda 2 0 0 0 0 0 0 lambda 2, and here let me rewrite it. It's not good in size, it's some problem. Let me write it in a better shape, something like this: 2 0 0 0, mu 1 2 lambda 1 0 0, mu 2 2 lambda 2 0 0 0 2. Okay, times m0 is 0, m3 is 0, so it just remains m1 and m2, and it should be equal to 0, d1, d2, and 0. But we know that some, in fact, materials for mu and for lambda and for d, okay? So I have to compute something. Let me write, we had mu j be equal to hj over hj plus hj plus 1, okay? Lambda j is equal to hj plus 1 over hj plus hj plus 1, and we know that dj is equal to 6 over hj plus hj plus 1. If you have no idea about these numbers, you can refer to my previous lecture. I have computed all of these terms. So here I will have yj plus 1 minus yj over hj plus 1 minus yj minus yj minus 1 over hj. Okay, so by this formula you can compute the values for mu1, lambda 1, mu2, lambda 2, m1, d1 and d2. How can we compute it? I know that hj equal to hj plus 1 equal to 1, because we know that hj plus 1 is xj plus 1 minus xj. And here, because we have some, in fact, nodal points with the equal distance, so hj equal to hj plus 1 equal to 1. Yeah, okay, now let me compute some materials. So mu1 equal to hj is 1 over 1 plus 1, so it's 1 over 2. Okay, mu2 equal to again 1 over 1 plus 1. So this one is also equal to 1 over 2. And the lambda 1 is equal to 1 over 2 and 1 over 2. So there is no change and everything will be 1. So this one is equal to lambda 2 equal to 1 over 2. It just remains for d1. d1 is equal to 6 over 1 plus 1 is 3 times yj plus 1. You have to use from here. y0, y1, y2, y3, 1 e squared, 1 e squared and e cube. Okay, so if you substitute instead of yj plus 1 minus yj and so on, finally you will get 3 times e squared minus 2e plus 1. And also you can find d2 equal to 3 times e cubed minus 2e squared plus e. Okay, now you have to put all of these numbers in the coefficient matrix and in the right hand side vector. So you can find a system like this. Two, 0, 0, 0, half, 2, half, 0, 0, half, 2, half, 0, 0, 0, 2. This is the coefficient matrix, and 0, m1, m2, 0. This is the unknown vector, and in the right hand side I have 0, 3, e squared minus 2e plus 1, 3 times e cubed minus 2e squared plus e, and 0. If you solve this equation, you can find m1 be equal to 1.5137 and m2 is equal to 11.6601. Now, you have to put these numbers in Sj. But if you put m0 equal to 0, m3 equal to 0, and m1, m2 from above in Sj of x equal to yj plus 1 minus yj over hj plus 1 minus 2mj plus mj plus 1 over 6 times hj times x minus xj plus mj over 2 times x minus xj squared plus mj plus 1 minus mj over 6hj plus 1 times x minus xj cube. Okay, so you can find S0, S1 and S2 as below. So S0 of x will be equal to 1 plus 1.4660x plus 0.25226x cube. S1 of x will be equal to 2.71827 plus 2.2228 times x minus 1 plus 0.7568 times x minus 1 squared plus 1.6907 times x minus 1 cube. And also you can find S2 of x to form 7.3890 plus 8.8097 times x minus 2 plus 5.8300 times x minus 2 squared minus 1.9433 5 x minus 2 cube. Okay, this is S0, S1 and S2. So finally, if you want to in fact see what is this figure, you have to plot S0, S1, S2 in the relevant interval, so you can find a figure like this. If you look at this figure, the red graph is for e to power of x. Okay, the red is for e to power of x. Let me try to write. Comment maybe here. No. Pencil. Here. The red one is e to power of x. Okay, but if you look from 0 to 1, the blue one is S0. Okay, from 1 to 2, the green one is in fact S1, and in interval 2 to 3, the light blue one is E2 is S2 of x. Okay, S0, S1 and S2. So you can have something in fact like this. This is a good example for finding the natural spline with solving a system of equation, and you have in fact a figure that show you how this spline interpolate a function. Let me stop here, and I will continue in the next lecture with one very important theorem. We call it Holiday theorem, and I will state and prove the theorem in the next lecture. Please support my channel by subscribing on my channel and watching online. Thank you, and wait for the next lecture.